Oh, I will share my screen. Let's see. Okay. So just to check, can everyone see my screen and hear the audio, the sound? I don't know how to make this chat window small now. Must be a feature. Okay. Anyway, so I'll try to. It's so laggy. Do introduction to gRPC first, and then okay, this okay. Anyway, yeah, I'll just go through the introduction to gRPC first, and then we will go into the reliable broadcast. Yeah, and just a few things regarding the labs. Most likely, and the exam, I have sent in a proposal to the exam office, and I'm still waiting for the formal approval. But if they approve my suggestion, then the exam will be changed so that instead of having a regular exam, you will be asked to write a project report. So yeah, as soon as they formally approve it, then I will let you know. And the plan is that you will be asked to read 3 or so research papers, and from these 3 papers, you're asked to write a comparison of the 3 systems and algorithms proposed in each paper. But yeah, as soon as I know for sure, then I will of course update you, and this will be, if it's approved, it will be 100% of your final grade. So this means for anyone that just wanted to redo the written exam and keep the 40% grade of the lab exam, you will not be allowed to do this semester. Only yeah, you must write this project report. Yeah, so that's that. I will. They told me that most likely within 2 weeks or so they will review it and approve it. All right. Then yeah, I just wanted to do a short introduction to gRPC because every semester we have some students that have some issues grasping this gRPC concept, and well, I can understand why, because it's kind of frightening, because when you if you want to read about this and you go to the official website, then you are kind of bombarded with information. So this thing that they call basic tutorial, it's people think that it's very long. It's maybe some people are giving up, but just rest assured that in all actuality, it's not that advanced, or let's say difficult for our purposes, at least in the lab too. And yeah, you're free to use this, of course, in later labs if you so choose. But the main objective of this gRPC is kind of illustrated in this simple figure here, that we have not the participants, but we have we have one server written in C++, and then we have two clients written in two different languages. So by using gRPC, we are allowed to more easily write clients in, or implement clients in different languages. And this is, of course, not the only way to do such a thing. I'm sure most of you heard about XML and JSON, and this is for sure different approaches to do this. And you can also write a binary encoder and decoder, or serializer and deserializer yourself. But if you use protobuf as the message format, you're kind of saving yourself a lot of trouble, because people have already tested out these things. So for the lab 2, you need to, we have now this semester, we have set, well, if we open lab 2 here very quickly, show you all the assignments proposed early. Lab 1, lab 2, lab 2. There's 3 main tasks here that you need to do some coding: UDP, web server, and gRPC. So to pass this lab, you need to actually do all 3 things here, and of course the question part. But we required 90% completion, and you will not be able to reach 90% if you don't do this gRPC part. And it's always amazes me every semester, because we have students that do number 1 and number 3, number 5 very well, but then somehow they struggle with gRPC number 4. And in really what this asks you to do, it's mostly just to install the packages and the the software and the gRPC software and protocol buffers. So I'll just show you how you can do that. Now I'm using Mac, so it will be a little bit different if you're using Windows or Linux, but the main thing is that you need to have Go installed. Obviously, that you should have had this from Lab 1, and then you need the what they call the protocol buffer compiler, and we will see what this is, but let's first off just see how to install this thing. You just open the installation link, and here it has different ways for Linux. You run this command. For Mac, you run this command. Or if you have Windows, you can just get the binary here probably. So easy enough. And if I run this install command, which is not this one, now I did this beforehand, but yeah, this is how I would start. Just write brew install, and it says, okay, now it's already installed to the latest version. Great. So then we go to the next prerequisite. This is the Go gRPC plugins, compiler plugins, or protocol buffer plugins for Go. So just type these commands in your console, go get, and that's it. Then update your path. You should already know what is this, but if you don't know what is your path is basically the directories where your terminal or shell will search for executables. So now I already installed this protoc here, as that you see. This mouse is there. And it has all the options for help. And if I want to see where is it, I can use this which command, and it's located in this folder, which is then part of my path. So all easy enough. Then to test your installation, you can either go through the instructions that are provided in the lab itself, or we can just try the what the gRPC documentation offers. They tell us to clone this repository and enter get basically the example code. And you see that I have already done this in my Visual Studio. Yeah, you can do this yourself if you want to. Then we can run this server. Just go run. When you do go run, you're building the code and then you're running it. So we can run the server and run the client. You see that it's answering back. But if we try to inspect the code here to see what happens, we will see a lot of strange things, perhaps. because now we don't have the what you would expect. Maybe we have something called a hello request, and this has a lot of fields here, a lot of strange tags that you might be unfamiliar with. So the main function here, it sets up a TCP listen server on the port that's specified here. Not so important. And then it runs the new server command from gRPC, and it's starting to listen for any incoming requests. And then it has one function here that just prints out the received message. So we can see that this server prints out this received message. So, you know, if we want to change something, we can do this very easily here. It will, we need to just compile again, and when we run the command, it will print our test message here. Yeah, we don't know. I didn't show you what is in this hello request. And if we just go through Visual Studio and go to this file here, it looks kind of strange, especially if you go down here. You see that there's a lot of hex codes in a long byte slice here, and yeah, in general, things that is well, everything here. This is written by this compiler or generated by this generator. So it says clearly here that we shouldn't edit this file, and if we want to add something to our server here, we need to actually always go to this proto file. So in the file that's called .proto, this contains the contract between the server and the client. So in this file that you can see yourself in the example, it says there is one service called greeter, and it has just one RPC command. This say hello, and it takes in one hello request and returns a hello reply. And the definitions for the hello request and hello reply, they are defined here. And if we go to the main, again, we can see that this is in fact what we are receiving in and what we are sending out. So if I want to have more things to either my request and reply, if I want to have another string, let's say, you can say like test, for example, and it can be something different here if we want. When we save this file, and if I try to use this now, like if I go to my hello and I'm getting the hello request, and I want to, for example, yeah, we can do this and whatever. And I want to have the second argument in my print. We will say, oh, I don't find this. Yes, I find the name, the get name, but I try to add another one called test, and it's not showing up. So what's missing from my steps there is that I need to generate this protobuf or this Go code using the protobuf generator. So the instructions for this are in the further down the page here, and they have an example where they are adding another RPC command. We can also do that. We can just copy the code that they have here to our photo file. Doesn't. Okay, I will copy like this. Great. And then you need to always, when you update the proto file, always run this generation command like this. So you don't need to worry so much about what everything does there for now. You can check this yourself. But the main thing is that you need to run this every time you change your proto file. You need to run this generator here. So I've already prepared this command. So it's here. The main thing is that you need to point to the proto file at the end here. When I run this command, it finishes very fast, and we see now that I have generated new classes here. Yes. So now I have a new hello request with both the name and the test, and also the hello reply will have the new fields. So if I now go to my code again, and with the IntelliSense here, yeah, if it was working properly, I should have got suggestion to use the new field that I generated, but maybe we need to open it again. Let's see if it will work as expected. Oh, okay. So maybe I'm missing one step here. But I really thought that I had. So there is get test. So this can also sometimes happen with your Visual Studio, that it's the IntelliSense is not working 100%. This is might be because what what's it called, interpreter you're using. Anyway, we can just never mind the language server here, and we can also do this in our client, that our client will not only also you see here that here in the IntelliSense is not showing the new field that we added to the request. We can just write them manually for now. So now we have extended the request, and we have done something with the handling of the request here on the server side. So if we try to build and run the server, it doesn't have any issues compiling, and the same with the client. It runs, and voila, now you see that I was able to send this message here to the server. Yeah, and then in the quick start guide here, they said that you can add or use the new service, RPC service that we defined in our portal file here. We can just paste in the code. If we do that, and also for the client. So the client is here. So if we do that, yeah, okay, now we have some issues here. Maybe it's always great when you have live demos. Yeah, I guess now I just pasted in the function into another main function. So this is obviously not the correct thing I wanted. So let's try again. Yeah, so again, the language interpreter is complaining that this doesn't exist. It can happen if you have issues with this. You can just restart the whole Visual Studio. Yeah, I don't know what. So right now I'm using this language server here. So the issue that it's not working properly might be related to this, because I just received a message that there's a new version. Anyway, yeah, now we run the client, and voila, you see it getting the message once again from, and also on the server side. Yeah, I guess we didn't print anything new here. Yeah. So, any questions about gRPC? This is really what you need to do in lab 2. Just in lab 2, you will be asked to insert some other commands, and you do this in your proto file. Afterwards, you run the generate command, and it will generate for you this pb.go file, and you then will use this in your own implementation. So any questions at all regarding gRPC? Because the deadline for lab 2, this is on Monday, and I think it's on Monday, on the 1st February. Yeah, so try to finish, so you will have more time for lab 3. And lab 3, it will be posted here during this week. Yeah. Okay. So let's go into the next part then, since there's no questions. Reliable broadcast. So yeah, this this chapter it's has a lot of sub chapters in the book, and today I'll try to finish with the first ones up to FIFO and causal broadcast. So anyway, let's get going. Broadcasting, I hope you're all familiar what is broadcasting. So in our vocabulary, we don't really make the distinction between multicast and broadcast for the most, unless it's very explicitly stated, then you can assume that when it says broadcast, it's really sending to all the other processes, unless they are crashed, obviously. So some example systems of this pops up that we discussed previously, and which is like that you have one or many listeners to an event, and then the publisher, once he published something with this event tag, then all the listeners or subscribers will be notified of this message. So this is a typical broadcast event, and we saw an example last time with the primary backup with some like we used the example that it was used for a replication system where the primary and the backups had replicated data, and in such systems we also saw that it's necessary that all the servers gets or processes the client command or the client request. So this is also another system that you will typically need to use broadcasting in. Unfortunately, this is not straightforward to use as point-to-point link, because even though if we assume that the links are reliable, like TCP-like, then we are still subject to many challenges. And the challenges, they come from the fact that we have to deal with asynchrony and timing, and also the Byzantine servers in our system. So, well, we have at least three main categories of challenges that we will see today. Is that the server or the sender can fail while he's sending the messages, and this can lead to that only some of the recipients receive the message, while others do not receive it. And then we have, in the Byzantine case, that if the sender is behaving maliciously, he can send different messages to some or all servers. And if your algorithm doesn't account for this, then your system can potentially be in an inconsistent state, because they process different, or they deliver different messages. Then we have the a thing with asynchronicity and timing, that if the server is broadcasting many messages, then it's necessary that they are delivered in the same order, usually, or it can be depending on the application. In some applications, the ordering is not important, but in others, it's very crucial. So this is all things to consider when we are looking at algorithms. Yeah, so here is a very simple illustration of a broadcast. The process P is broadcasting something to the other processes, Q, R, and S. And you will see here that there is one black arrow and one, or some black and some white arrows. So the black arrow, it means that now the message is delivered to the process, and then the white, it's I mean that the white means that the message is delivered by the process, and the black symbolizes that the message passing. So the message flows to, for example, from P to Q, and then afterwards Q can deliver this message, which if you remember, that this means that the BEB, best effort broadcast layer, processed this message, and it delivers this up the stack to, for example, the application for another layer above. Yeah, so this is the module description of best effort broadcast. It broadcasts the message M to all processes, and it also delivers a message that has been broadcast by a process. So here we are talking about the crash stop. Yeah. Oh, what happened now? I can random updates going on. Can you still see me? Did I lose everyone? New shows, posture. Yeah. Yes. How does it work that my mouse is invisible? What's the deal with this? I will try to somehow stop sharing. Yeah. Always interrupted by something. Ah, okay, now I see the mouse. Great. Do you all see this screen still? I will try to restart the presentation. All right, great. Sorry about that. Okay, so yeah, best effort broadcast. This is in the crash stop scenario, and or let's say crash stop assumption that the process can either be crashed or it can be stopped. So let's see, we have three properties, and what you will, for example, as I mentioned, that you will need to, or hope, I think if they approve that you will be asked to write this project report, and in this project report you need to do an analysis of the algorithms that is proposed in the papers. So it will not be in probably not this exact format, but it will the algorithms will most likely write or define some properties that the system that's proposed or the algorithms that are proposed offers. So for this module, we have three. We have the validity, we have the no duplication, and we have no creation. And what is a good tip for you is that you classify these properties depending on if they are a safety property or a liveness property. So remember that safety property, this is something that ensures that your algorithm is behaving correctly, that it's not doing something bad. And the liveness classification, this is something that ensures that your algorithm actually does something. So in this example here, we have two safety classifications. This is no duplication. So no message is delivered more than once. So obviously this is, or let's not use the word obviously, but this is ensuring that nothing bad happens in your system, because it would be bad if messages could be delivered more than once. So if the message could be delivered more than once, then you would be subject to that your system is keep on processing the same message indefinitely. And the no creation property, the no creation property, this is also a liveness classification, because that no messages are created out of thin air. So only if a process delivers a message, then this message was sent by someone else. So it can be more easy for you to think about what are the safety properties first, and once you have like classified all the safety properties, then you know that the rest must be regarding liveness. So if we think about number or property 2 and number 3 here, then if our system didn't was no creation safety or liveness? Oh yes, I mean that both no duplication and no creation are safety properties. Yeah, both number 2 and number 3 are safety properties. Yeah, good question, because I don't want to confuse you with this. Yeah, both of them are number 2 and number 3 are safety. And we can easily see this if we think about what would happen if our system didn't do anything. If we started the system or started this algorithm and we didn't send any messages at all. We didn't send any message and we didn't receive any message. So in this case, both the number 2 and number 3 would hold because we are only interested in nothing bad happens. So this is how I tries to think about it. And then since we now know what are the safety properties, then the last one, validity, this is about liveness. So this one states that if a process broadcasts a message, then all the correct processes will deliver it. All right, so we can see the algorithm for this, and maybe you are surprised that the algorithm is so short because now I talked for 10 minutes and then the algorithm, it's basically in 5 lines here. But the key thing here is that it's using the perfect point-to-point links that we saw previously, so that everything that we discussed regarding perfect point-to-point, it still holds for this algorithm. So the perfect point-to-point links, and then the stub-on links and the fair loss links, they are all underneath this level. Yeah, if you were asked to draw the module composition, then this is key information. So yeah, you will see this just has the event when the application layer triggers a broadcast with a message M. It just loops through all the processes that it knows about, and it sends triggers a send event on the perfect point-to-point links underneath. And when the perfect point-to-point link delivers, then the best effort broadcast will deliver up the stack. So what is the problems with this algorithm? First of all, you will see that what happens if we crash halfway through this loop here. Then we have just sent the broadcast to half the processes. This is not good. And also we have no safety mechanisms to ensure that we deliver yeah, we rely on the perfect point links to ensure that we deliver only once. Yeah. So we already saw this. This is what will happen in the best case if everything is working out as expected. But what I said before, that the process 1 here, it's working well when it's sending message to the message 1. And by the way, one thing that's not so obvious is that we in this algorithm, and for all the other broadcast algorithms, then our self is also included in this P. So we are also sending this message to ourselves, which is kind of counterintuitive if you would do this in programming, you would probably not send it through the network to yourself, but in the description of these algorithms, it's important to realize this fact that we are uh, ourselves also in this set of all the processes. And this will be useful for um, um, algorithms down the line. But this is why you see this deliver processing here, because the P1, it broadcasts the message M1, and it's also delivering it itself. But we have a problem here if the process 1 crashes before the P3 was able to receive it, or the link was broken perhaps. Anyway, the important thing is that the best effort broadcast, it can easily lead to an inconsistent system state, because in this scenario, only process 2 has delivered the message. So this means that process 2 is in a different state than process 1 and process 3. So what can we do about that? We can have what we call a regular reliable broadcast. And this has the same events, broadcast and deliver, and it has the same properties 1, 2, 3, validity, no duplication, and no creation. Well, I just want to show you very quickly here that we have the node duplication, and if you saw in this algorithm here, it's not obvious that this has node duplication. Like we see no code here for node duplication. So what actually is happening is that the level underneath the I don't know, maybe I have the presentation here. For the, if we go to the perfect point-to-point link, we will hopefully see this if we are lucky. So yeah. So if we go to the perfect point-to-point link module that the broadcast abstractions are using, we will see these two properties. Yeah, and especially the new node duplication property. This is handled here. That here you can actually see that from yeah, and then if we go to the stubborn link, here in the stubborn link properties, we don't see this property with no duplication, right? So the first time we see this in our stack is in the perfect links or reliable links. And it's just this code here, so that we are, the perfect link, it's checking that the message that it received hasn't been delivered already. And if we go back to this best effort broadcast, it's just using this perfect point-to-point link. And this is why it can also offer this property. So this is an important thing to consider always when you're like when you will be asked to analyze the algorithms. Anyway, yeah, we were just talking about the regular reliable broadcast. And the new thing here is the property 4. If a message M is delivered by some correct process, then M is eventually delivered by every correct process. So this property here, agreement, this is a way to ensure that or an attempt, a basic attempt to ensure that the system will be in a consistent state. Yeah, this is one example execution that if the first process delivers, then all the other processes must also deliver this message, even if the first process crashed. Here is another scenario that, yeah, message 1 is sent, and everyone delivers it, but it's sent to process 2 and process 3, and since process 2 delivers this message, then also process 3 must deliver it. Here it's important to know that this is a correct execution of the algorithm, because P1, there's no requirement for P1 to deliver this message because he is crashed. So the regular reliable broadcast doesn't provide any guarantee for faulty or crashed processes. Here is another example execution that no one delivers the message to. So both of these scenarios is possible. Just our agreement property here is stating that if it's delivered by some correct process, this only triggers if the message is delivered by some correct process. Then it will be delivered by all the correct processes. But this also holds if no one delivers it. All right, is it clear? Then we will have two implementations, possible implementation of this module, and I hope you're familiar with lazy. What does lazy means when it comes to programming? It doesn't mean like lazy programmer, but it means that you know, I don't know the formal definition of lazy, but it means that usually you don't do something until you need it. That you're trying to optimize your algorithm by only doing some in process intensive step once you need it. So it can be sometimes you will have a lazy initialization, meaning that you will, for example, only initialize some array or some dictionary once you actually need it in your algorithm, but otherwise you will just keep it null. So this algorithm here, it has the lazy, the thing what is lazy about this one, it's that it will retransmit the broadcast if it detects a crashed sender. So here this is the first time we see an algorithm that has two dependencies, like it's using the best effort broadcast that we just saw, and then it's also using the perfect failure detector that we saw last time. So if we were to draw this module composition, it would no longer be a very beautiful stack. It would be two stacks, or it will be two things probably. And also we have three events here. So the broadcast event, and yeah, the broadcast event comes from the application, and then deliver goes also to the application, and then from the reliable broadcast, and then the best effort that goes one step down the stack, for the broadcast, and then for the delivery it comes from one level underneath. And then on the side, like in the second stack, we have from the leader detector that we have an additional event that triggers the reliable broadcast, which then triggers the best effort broadcast. So yeah, if we want to see very quickly what does this algorithm do, we can just maybe see here first when it detects a crashed process, like a process that is crashed. It removes it from its correct set, and then it's iterating through all the messages that it has received from this crashed process, and it's broadcasting them again. And on the deliver event, it's then making sure that it's like filtering out the messages that was received from a particular process, so it's not processing them again. Yeah, and then once it's delivered up the stack, it's updating the stack, yeah, or the slice or the array of messages from this process. Yes, and it works like this. So yeah, as I said, when it's lazy, reliable broadcast, it only retransmit the message if the sender has crashed. So in this scenario here, P1 is sending the message M1 and to process 2 and process 3. And for some reason, the message M1 is lost, but P1 and P2 is able to deliver this message. But once P2 detects that P1 is crashed, then it will broadcast the message M1, and then P3 is able to process it. So here, this algorithm now ensures the agreement because one if one correct process was able to deliver the message, then all the correct process must deliver it. And then in the second execution example, let's see, what do we have here? We have the same thing. The M1 is sent, and I wonder if I was I was a little bit fast here, because this is actually I think an eager example of eager reliable broadcast that we will look at next. But when it's not lazy, it's eager. It means that it whenever it delivers a message, it will directly broadcast it. So we can, just for the sake of it, update the description here. Broadcast any message that was delivered. So this is what the eager version of this regular reliable broadcast will do. And still here we ensure the same agreement property, that if one correct process was able to deliver the message, then all the correct process will deliver it. But here we have some important analysis that we could do, and then something that is valuable and expected from you to put in your project report. And it comes down to what are the overhead, or what is the performance of these algorithms. So if we just count how many messages are sent, we can see here it's 1 and 2, 3, 4. Here it's 1, 2, 3, 4, 5, 6. So we can clearly see that this algorithm, it sends more messages, and we can very easily see that this would be a big O of n squared type algorithm, because you have for every message that you send, if you send to P1 sends to n processes, then each n process will send to another n process. So you have kind of like a n multiplication with n messages that are being sent. So this is something very important to put into analysis. Yeah, the algorithm for this, it's simple enough. Whenever you deliver, if you already didn't deliver this message, you trigger another broadcast. So whenever you get or you deliver a message, if you didn't see this message before, you will broadcast it to everyone else. And remember that the purpose is to ensure that if one correct process delivers the message, then all the correct process will deliver the message. Here we have, what do we have here? Here we have a faulty execution, right? Because this is something that could happen in the regular reliable broadcast that we saw. Because in this, in our this example here, we have a P1 sends a message M1 and all the processes deliver it. Then later on it sends a message M2 and it delivers it itself, and P2 delivers it, but the message M2 is lost, and so it never reaches P3, and before anyone is able to retransmit, then they have already crashed. So now we have an inconsistent system, and it's easy to have the view that but this doesn't matter because they are crashed anyway. Maybe if P1 and P2 are crashed, what does it matter that they have a different state? But it is very important because there might be, for example, clients or different servers or processes that attaches to P1 and P2. So in this example here, you could imagine that that they have already replied back to a client or to different things outside our system here, and it's not it's very bad because P3 doesn't have the process doesn't have the same state. So we really want to avoid this situation. So what we can do is to have the uniform reliable broadcast abstraction, and the whole point here is that we no longer are talking about agreement between message that was delivered by correct process, but also faulty processes. So it no longer there's no difference if a message was delivered by a correct or faulty process. What this uniform reliable broadcast ensures to us is that if any process delivered a message M, then this message M must be eventually delivered by all the other correct processes. And how could we achieve something like this? It's not maybe so obvious this thing, because how will the rest of the system be able to learn about messages that was delivered by faulty processes? So the key thing to keep in mind here that for this and all the other protocols that we discussed, there is some agreement. So agreement, this is the translation is the understanding is that before a process does something, it must agree with the rest of the system. So we cannot allow that some processes just do something without first agreeing with the rest of the processes. So so this is the scenario that we had before, right? And actually, I think that Yeah, let's just be sure that this is for regular reliable broadcast. But if we are talking about a uniform reliable broadcast, then we need to ensure that also the P3 here delivers this message. So obviously the fix is not to, or the algorithm is not to fix this network link here. So what would happen is this here, that P1 again sends the M1 message, they all deliver it, and then it sends the M2 to P2, and if they crash before they deliver it, then nothing more will happen in the system, because we cannot allow that one process is able to deliver and the others are not. So again, here we have we have a non-uniform example. So it's important to be clear about what is uniform and what is not uniform, because here we see that process P and Q, they deliver the message, but R and S, they do not. So this is not a uniform reliable broadcast. So we can just, I can update the header here. Yeah, and the algorithm for this is here, but let's first, before we see the algorithm, maybe we can see the sequence flow. And also this is something, I will write what you must put in your project report, but things like this, you know, we have this long algorithm, but if we have the figure here, we can instantly see what happens. So for your report, don't be shy on giving us figures. Yeah, we will see this algorithm here afterwards, all ACK uniform reliable broadcast. But the idea here is that when P1 sends the M1, then there is a second phase of this algorithm, the execution of the algorithm, which is typically called the agreement phase. So you can imagine that there are two phases here, like the initial phase where the M1 is proposing a message, and then there's a second phase where they agree to deliver this message. And this type of flow will be more familiar to you, and you will see this again and again in the consensus algorithms that we will discuss, and Paxos and so on. So here you can see that what can you see here, that all the processes that they deliver, they have received the M1 from the two different processes. So P2, he has learned about M1 from both P1 and P3. And similarly, P1, he has learned about M1 from P2 and P3. and P3 has learned about it from P1 and P2. So when they have seen this, they know that actually they know that all the other processes in the system know about this message, and then they can safely do the deliver, because they know that now everyone has seen this message. So it's important here to also think about the fact that the M1 here from P1 to P2 and the M1 from P1 to P3, it would be more optimized if P2 also included to P3 that it had seen the message M1. So, yeah, this is for now just something to think about. Yeah, and then we can see the algorithm here. What are the interesting part here? The can deliver function. So it's a Boolean function that it will return true only when it knows that the message M has been seen by all the correct processes. So the ACK here is the acknowledgement, and first well, we can see that when the process receives or delivers a message, it updates this ACK for the message, and then with the key the process that sent it. Yeah, and then let's see, what is this pending? So the yeah, if it's not already pending, yeah. So if this is to ensure that we only deliver it one time. So remember that, yeah, if we had more, yeah, we can see here that the P1 it sends to P3, and after this it broadcasts. But once it receives the message from P2, it will not broadcast again. So this part here with pending, this is to ensure that we only broadcast this message one time. So the yeah, and then the last interesting part here, if we have broadcasted this ourselves, that meaning that we are in the pending set, and we have the can deliver function return true, and this message was not already delivered up the stack. Then we add it to our delivered set and deliver up to the application. Is this algorithm clear for everyone? All right. Great. So what this will allow to us is that now we can have this scenario where the P process crashes and the other processes can deliver still. So remember that this process or the module description, it just guarantees delivery by the correct processes. So it doesn't guarantee that it will be delivered by a faulty process. So this is why that it will not guarantee that the P can deliver it because it's crashed. But you see that? So another implementation, we can have this thing that we discussed last time with quorums, that if we are in asynchronous environment or in a fail silent abstraction, then we can not rely on a failure detector. So instead of relying on a failure detector, we can redesign the can deliver function so that we will deliver the message if a majority of them or we have received a majority acknowledgement. So the hashtag here, it means to cardinality. So well, now we are kind of out of time, but so I think we will stop here, and then we will continue with stub-on broadcast next time. I will go through the stub-on broadcast, logged best effort broadcast, the logged uniform reliable broadcast, more fastly than the broadcast abstractions that I discussed today, because this is similar things, just in different timing models and different process abstractions. And then we will go on to probabilistic broadcasting, and after that we will go to the FIFO and causal broadcast, and then we will you will start seeing consensus algorithms, or what we call consensus algorithms. Because remember now that we have this this guarantee here that the processes will only deliver the message once they are sure about that the rest of the network has also delivered it or seen it. But what we are missing here from a consensus algorithm is an agreement on the ordering of messages. So if P1 here were to send the M2 and M3 and M4, there is no guarantee provided by the uniform reliable broadcast that the messages are delivered in the same ordering. So this is the things that we will start to see next time, that to ensure that we do not end up in an inconsistent state. We also need to have some guarantees about ordering. All right. Okay. Any questions so far? One thing that I checked is with regard to the slides, and the only way that you will see the slides is that if you come to the lectures or see the YouTube video, because yeah, I'm just copying this algorithms here from the book, and you have the book on PDF, or you can get it if you want for free. So I don't want to have any issues where I'm sort of distributing the contents of the book. So that's why I will not share the slides, but you can see them on the video, or yeah, and you should get the book so you can study these algorithms for yourself. Okay, so if there's no questions, we will continue on Thursday. Okay, thanks for now. Yes, I provide the videos. They are in the, maybe I will show to you all here. You can go to the course info. If we go to the course info, and can go to the lecture plan. And here I have updated the first 5 lectures, and I will update with video for today. And there's a playlist here that if we open the playlist, then you will be sent directly to the YouTube playlist. And I will try to put the YouTube video here after each lecture. All right. Okay. See you on Thursday.